go number 4. Okay, knowing the integral from a to b of x is b squared over 2 minus a squared over 2 for a less than b, and the same kind of information for the next two, we want to find the following. The integral from 0 to 2.5 of x dx and 0 to 0.3 of s squared ds. Okay, so for part A, it looks like we're going to use actually this first rule right here. Because it says that I'm going to take the integral of just x dx, and as long as a, which is 0.5, is less than b, which is 2.5, then I just use that formula. Well, that'll work. We can easily plug that in. 2.5 squared over 2, that's my b over 2 squared, minus a, which is 0.5 squared over 2. Okay, so when we just do that math real quick, and we'll get an answer of 3. So the area under the curve of just x dx from 0.5 to 2.5 will be 3. All right, let's look at the same thing with the second one. It looks like we're taking a integral, a definite integral of s squared. So it looks like we're going to use the third rule here. And if a is less than b, which it is, so it's going to be b cubed, so 0.3 cubed over 3 minus a cubed, so 0 cubed over 3. And simplifying that out, we'll get a overall area under that curve from 0 to 3 of 0.009. Okay, so it looks like we're going to have to use those rules some more. Let's see what we can do for part C and then part D. And part E, we got lots going on here. Okay, so we're going to do the integral from a to the cube root of a, or cube root times a, of x dx. So let's check. If a is right here and the square root, why did I say cube root? I don't know. And if the square root of 3 times a, that's definitely larger, right? Because the square root of 3 is 1.7, so you're magnifying a by emphasizing it more by a power of 1.7, so that definitely works. Okay, so let's go back up. So the property of just x dx, you're taking the integral. It's that very first one. So it's going to be b squared over 2 minus a squared over 2. Okay, so b squared, square root of 3a over 2 minus b squared over 2. So cleaning this up, it looks like 3a squared over 2 minus a squared over 2. Got common denominators, so we can go across the top. 2a squared over 2, which is just a squared. All right, looking here at part D, we're looking like we're taking the integral, the definite integral of two things here in our brace. So let's break it down and see what we can, if that helps a little bit. We're going to take the integral from 0 to the square root of 2 of t dt minus the integral from 0 to the square root of 2 times the square root of 2 dt. Okay, well, this first part is just the rule we've been using before. Okay, since a is less than b, and it's just like t dt, like x dx, it's going to be the top one, so square root of 2 squared over 2 minus the bottom, which is 0 squared over 2. All right, now minus, and let's look at this next part. We're basically taking the integral from 0 to the square root of 2 of a constant. And if we go back up here just real quick, we're looking finally here at the second one that we haven't used before yet. Since I'm taking the integral from a to b of a constant, c, it's just going to be that constant times b minus a. So it's going to be the square root of 2 times, let me write this out, square root of 2 minus 0. Okay, so cleaning this up, the square root of 2 squared over 2 is just going to be 2 over 2, which is 1, minus 0, that all goes away, and the minus the square root of 2 times the square root of 2 is 2. So the overall answer would be negative 1. Okay, so let's box that up and go on to part C, or part E. Looks like finally the last one of the group. Okay. So far, all those rules, we've had to have our lower number, our lower limit, smaller than our upper limit. So right away, the first thing I think of before I even start this problem is I want to swap that around. So let's make it negative, then 0 to 1 of 3x squared plus x minus 5, then dx. Okay, and then from there, let's divide it up into each piece. So it's going to be the negative integral from 0 to 1 of 3x squared dx minus the integral from 0 to 1 of x dx, and then plus the integral from 0 to 1 of 5 dx. So using all of our rules, let's pull off that negative 3, and this is telling you of x squared dx. Then what we're going to do for that one is start incorporating our cubes. So it's going to be that upper one, so it's going to be 1 cubed over 3 minus 0 cubed over 3. Again, that one just because I pulled that constant out front, okay? And then minus, and this one's here's that typical x dx, so we're just going to use the upper bound squared over 2 minus the lower bound squared over 2. And then this one was the one we just used on pretty much on example D, that middle one, where it's our c value, so it's 5, just times 1 minus 0. Okay, so cleaning this up, it looks like we can take that one away, we can take that one away, and we don't have a whole lot left to work with. So negative 3 times 1/3 would be negative 1 minus a half plus 5. And putting that all together, we can either say 3½ or we can say 7/2. And there's our answer. Okay, example 5. We want to use a definite integral to find the area of the region between y equals x over 2 plus 1 and the x-axis over the interval from 0 to b. If we looked at this kind of like the same problem like we were doing in the last section, what we would do is, in order to find, because we don't know how far we're going to go, we just know it's just b, but we would, to find our areas, we're going to divide up each of the areas into those rectangles. We would find that the areas are going to be the difference, so b minus 0 over n. We were trying to find so many subintervals, which would just be b over n. So that's normally what we would do. And then we would draw the rectangles and kind of do the upper limit through everything. Now we can look at it as we can actually write some stuff down. So it's going to be the integral of 0 to b of our function, x over 2 plus 1 dx. And now we can kind of work with it just a little bit more. So we can say the integral from 0 to b of x over 2 dx plus the integral from 0 to b of 1 dx. Okay, so working with this again, we'll pull off that 1/2 0 to b of x dx, and then I'll leave the other one just the way it is, so 0 to b of 1 dx. Okay, and using the properties we just did in the last several examples, the integral from 0 to b, when specifically 0 is definitely smaller than b, it's going to be b squared over 2 minus 0 squared over 2. And then the integral from 0 to b of a constant is just your constant times b minus, not a, but b minus 0. Alright, so further cleaning this up, we have b squared over 4 plus b. Okay, so what we have just found is basically the area under the curve for this equation right here over the interval from a to b can be represented by b squared over 4 plus b. So all you have to do is have somebody tell you the upper limit. Let's say all of a sudden, let's take the area then from 0 to 9. All we have to do is come in here and plug in 9. So get 81 over 4 plus 9, and right away, just like that, you already know the area. So this is just a general formula. So as soon as you find the upper bound, then you're good to go. All right, example 6. We want to graph this function over that interval and find its average value. Okay. Well, real quick before we do that graph, let's write that average value formula. Okay. Average value is going to equal 1 over b minus a times the integral from a to b of our function. Okay, so now let's start looking at the graph. Okay, so looking at the picture of the graph, we basically have a parabola, a portion of a parabola coming in, and we want to find then eventually this area that's kind of cutting down through there and through here. So it's all going to be in there and then all going to be in there. And we want to find actually the average value of all of that. Okay, so if we just go with the general formula, it's going to be 1 over the upper bound, so there's b and there's a, so we're going to go from a to b. So 1 minus a negative 2, and then the integral from -2 to 1 of our function, which is t squared minus t dt. Okay, so together that's going to be 1/3. I'm going to break this up. So -2 to 1 of t squared dt minus 1/3 times the integral of -2 to 1 of t dt. We've got rules for that one. We've got rules for that one. We've got 1/3. Okay, when I do the rules, it's going to be, let's see, it says it's the upper bound. So 1 cubed over 3 minus the lower bound. So -2 cubed over 3 minus 1/3. And then for this one, we have that rule that says it's the upper bound squared over 2 minus the lower bound squared over 2. All right, so let's clean this up. 1/3 times, let me go and write it like this, 1/3 times 1/3 minus 1/3 times a -8/3 minus 1/3 times a half plus 1/3 times 4/2. Okay, so 1/9 plus 8/9 is 1. 9 over 9 is 1. And -1/6 plus 4/6 is 3/6. So 1 plus, basically 1 plus a half. And our answer is either 1 1/2, or if you want to write it as 3/2. Either way. And right there is the average value for the function. So let's go on and find our answer to our last problem. With this example, we want to find the values of a and b. They're going to minimize the value, so we want to find the minimal area for that curve. Well, to really answer the question on what values of a and b are going to minimize the values, well, minimum values are going to occur basically is where the integrand is going to be the negative. So where is x to the 4th minus 2x squared negative? That's really what it says. That's what's going to give us the minimal value. When we say by negative, we mean really technically below the x-axis. Okay, so one of the easiest ways to do this, obviously, is let's draw the graph of this integrand, of this function, and figure out where is it below the x-axis. Okay, well, as I draw just a general idea of what that graph looks like over here on the left, it looks like it's below the x-axis between this x-intercept and this x-intercept right there. Okay, so let's go ahead and find our x-intercept then. So 0 is equal to x to the 4th minus 2x squared. So if I factor out that x squared, you'll get x squared minus 2. Okay. And setting each of those equal to 0, we get x squared equals 0, or x equals 0. And then x squared is equal to 2, or x is equal to plus or minus the square root of 2. So right there, that's two x-intercepts. So if a, which is if your lower bound, is the negative square root of 2, and b is the positive square root of 2, then that pairing right there is going to give you the minimal value of that integral right there. Again, if it said the maximum value, we probably wouldn't have this graph, or the graph would have been reversed, flipped over the x-axis. And so if it was that way, in the sense if it was coming up like this, then it would ask us to maximize the value, and then again we would have said from -2 and 2, because that would have given the only part of the graph that would have been above the x-axis. All right, well, let's call this quits for right now. Let's go on to the next lesson.